frequencies are short wavelengths. So it's probably, again, I mean, if you're not as familiar with transmission lines, it's probably a little weird to hear wavelengths when referring to circuits. But, excuse me, when referring to if we have a frequency, right, our frequency is composed of a signal that is electromagnetic, right? It's voltages and currents. So it propagates through the circuit at the speed of light. So it has a wavelength. Except in most circuits, they're so small, this wavelength is massive, so it doesn't really look like anything happens. So it's just one thing to think about, and I'll show you. So yeah, your smartphone normally operates on frequencies of several gigahertz, like 2.4 to 5 gigahertz, and actually go much higher with 5G now, actually. And RF principles are used for much lower frequencies. So this is a bad definition because it doesn't, like, what do you mean by high frequency? So amateur radio enthusiasts operate on bands as long as 2,200 meters, right? So 135 kilohertz. Now think about how massive an antenna you would actually need to be able to transmit. And the cool thing about these antennas, as I'll show you right here, these are HF antennas. They're actually on the order of 10 to 100 meters. Is that because the wavelength is so long, it has this really cool effect with the atmosphere where it's able to bounce off the ionosphere, and you can talk to people across the world. It's called DXing. It's really cool. So if you're here, our Ham Radio Club actually would make multiple contacts with people in Japan just by bouncing off a wave off the ionosphere back down to the ocean, and it kind of go back and forth until it reaches a receiver. It's really fascinating. And the cool thing about these really long wavelengths too is that they actually propagate on the surface of the Earth. They follow the curvature of the Earth, and then you can talk to people like thousands of kilometers or hundreds of kilometers away. So RF is used for massive antennas, massive wavelengths like this still. The same concepts still all apply, right? Everything that I will teach you still technically applies here, right? It's just the scale's different, right? So just thinking about RF as exclusively high, this is kind of not real, it doesn't make any sense, right? So we have to be a little bit more meticulous when we're kind of characterizing our system, or like what we mean by RF. And you also hear like stuff like millimeter wave, RF, and like distinction there. I mean, there technically is a distinction. Millimeter wave just means like the wavelength is like in millimeters or something, right? You hear like terahertz, right? Our frequencies at terahertz. All the concepts still technically apply. The physics is all the same for all those frequencies. So I honestly don't really see the distinction that much. I guess at terahertz we're not really doing much radio, or we're kind of doing visible light. But yeah. So what's a better definition? RF refers to circuits for wireless communication. It's in our case, that's the definition that we need. And a longer definition is that it's just a circuit operating wavelength that is small relative to the size of the circuits. Electromagnetic effects, parasites, and special design techniques must need to be accounted for. Right? So that's the entire field. Right? It's the so-called black magic. Right? You hear about RF, people just talk about it being black magic all the time. It's because you no longer can really think about just voltages and currents as these static things. It's really just waves propagating around the circuit. And you get some really weird effects and some really weird structures. And it's actually kind of like what these are on the right of the slide. These are actually kind of like modeled off of microwave PCB structures that you see. There's like really funny looking geometric structures. You know what they do, but they're just like funny looking. And so that's why they call it black magic. You look at it, you're like, I don't know what this does, but it looks cool. So anyway, basically any circuit operating 3 kilohertz to 300 gigahertz can be considered RF, and that's actually what I actually believe kind of awesome. So yeah, 300 gigahertz is like this ridiculously high right now. Maybe it's getting like 6G territory, or the next iteration of 5G, but we don't have to worry about that for rap. I don't think we have 300 gigahertz level equipment lying around. Anyway, yeah, so the size of the circuit relative to the wavelength is important. A good RF design engineer knows when to consider these effects. A good rule of thumb is that the circuit size is just greater than 1/10 of the wavelength. You might see some effects. Okay. So what do we mean by RF? Okay. Continue. Alright, so here is our actual RF system in its entirety. What wavelength do we operate at? Who knows this? Who can kind of calculate this in their head? So we're at 27 megahertz. Who can kind of figure this out? Maybe ballpark, right? So So the order of like maybe 1 meter, 10 meters, 1 centimeter.
Is that be like around 10 meters?
Yep, around 10 meters. So our wavelength is 10 meters, right? That's actually massive. Okay, I'm gonna be quite fair. Our circuit is like not, I don't think it's 1/10 of 10 meters even. So I'll tell you why we care, right? It's around 11 meters actually, right? But 10 is a good guess. It's around 30. And a really good rule of thumb, by the way, for wavelength calculations, that if you ever ask an interview, like, what's the wavelength of something given its frequency? Remember, 30 over the frequency in gigahertz will give you the wavelength in centimeters, right? So if I have a 1 gigahertz signal, right, 30 divided by 1 gigahertz gives me 30 centimeters. So 1 gigahertz signal has a wavelength of 30 centimeters, right? So it's like a really easy way to calculate these things. Anyway, so how large the ratio distance is compared to this wavelength? Well, it's 20 of the wavelength. It's very small, actually. So you might ask, well, why do we care about these things? And the truth is that like the actual like wave nature of stuff isn't as apparent in our circuits, and that's actually a good thing. We want that. We've actually designed our system to be really small like this because as soon as we start accounting for that, it just gets a lot harder to make the circuits themselves and a lot more expensive, right? So we kind of like teeter on the edge, right, and deal with all the parasitic and stuff. And we're still measured like an RF system or a microwave system, but it's just that it's actually it just makes it a lot easier for us to work with, and that's you're honestly gonna like that rather than hate it for what it is. Because if we were doing something a lot more complicated, it'd just be kind of a headache without proper equipment, which is deceptively expensive. Okay, so now we can move on to units. Decibels. All right. So let me just very quickly define what a decibel is for you. Who's seen decibels before? If you want to raise your hand. Hopefully the majority of you, thank God. So just to quickly talk about, right? So it's for some unit of this ratio x, its value in decibels is just 10 log 10 to that ratio. Decibels are inherently unitless. This is something you must remember. Right? When I say decibel, there is no unit attached to that, really. Right? When I say units, it's like kind of weird. It's like unit decibel is decibel, unit, whatever. It's just a ratio, right? So if I put something in here that's like, let's say, 10 log 10 of 1 watt, that's meaningless. You're taking a logarithm of a watt. Like, what does that even mean, right? It needs to be the ratio of like 1 watt to 1 milliwatt or something, right? So the units cancel out. So frequently we encounter the products of gains and losses in R, right? So logarithmic units like decibels are actually incredibly important because it changes our gains and losses, our products and divisions into sums and subtractions. So it's really easy to do math in our head to figure out what's going on in a circuit, for instance, or what level this is and what that is by just doing sums and subtractions. Or addition, subtraction, whatever. Anyways, so it allows also for much smaller numbers to represent very large numbers, right? For a logarithmic spectrum, if I have 100 in linear units, whatever, it's 100. If I have 100 dB, that's massive, right? That is 10 to the 10, okay? So it's like 10 billion. Right? Similarly, it goes for, minus 100 dB. Same idea, right? 10 billion. So you can, with just from minus 100 to 100 dB, you can get a massive range of values. So it's really, all the math you're doing is this addition and subtraction in that range. It's very easy to do on top of your head, and that's why it's in interviews, it's brought up a lot. Because you can get a lot of really nice on-the-fly questions. So here's one definition for power gain, right? So we say the gain in decibels is just 10 log 10 of the power out of something versus the power in of something, right? So this gain can be positive and negative too, right? Positive and negative. If it's negative, that means decibel negative, right? So that means that we have P out less than P, right? It's positive and P out greater than P, right? And then we have power gain in terms of voltage, which is also very important. So if we have a constant impedance V naught in the circuit, right? Remember that the time average power is V squared over 2R, or 2Z. So essentially we can just divide those two, right? And we find that we get 20 log 10 of V out over V in. So here's another thing. If you have voltages, right, you want to use 20 log. Because usually we're dealing with powers when we're multiplying things together and not voltages. So power is proportional to the square of the voltage. So the square comes out a logarithm, we get a 20. So that's something very important. So when you never get confused between 10 and 20 log. Okay. So here's some absolute decibel units. Now that is kind of contradictory to what I was saying earlier, but there are some standard decibel units that we use all the time that are absolute. They're in reference to something. So we have decibel milliwatts, dBm. We use this all the time, and this is our primary our units for power, right? So I'll say I have a 10 dBm source, right? So that means I have an oscillator which outputs power at 10 dBm, right? So what that means is that we just reference our power to 1 milliwatt, right? So if we have 0 dBm, that means 1 milliwatt. 10 dBm, that means 10 milliwatts. 20 dBm, here's what that is in milliwatts. Can anyone guess, figure that out?
Whatever the square of that was.
The square of it? Well, what we did is we added 10 to 10 dBm. So 10 dBm plus 10 dB gives us 20 dBm, right? So 10 dB is 10 times 10. So we actually get 100 milliwatts, right? So 20 dBm is 100 milliwatts. Okay, decibel watts. In reference to 1 watt, you'll notice it's dBm minus 30, right? Because 1 watt is just 30 dBm. Okay, and then we have decibel volts. So similarly, we can relate our RMS voltage, some RMS voltage to RMS 1 volt. And again, you see the 20 there. It's very, very important. If you're doing voltages and currents, you have to put a 20 there. Okay. All right, so who wants to answer this? What is 2 in dB? Does anyone know this off the top of their head? 3 dB? Yeah. So it's about 3. It's like 3.01 or something dumb. But like, it's basically for all intents and purposes, it's 3 dB. What is 10 in dB? 10? Yeah, 10. Okay, it's pretty simple. What is 4 and 5 in dB? Can you even figure this one out?
Is that 6 and 7?
Yeah. Okay, this is really helpful though. This is like a deceptively helpful example. So we have 3 dB plus 3 dB, right? So 4 is 2 times 2, right? So we have 2 is 3 dB. We multiply it by 2, another 2, right? That's another 3 dB, right? So that's 3 plus 2 gets 6. 5 is a little bit less obvious, right? So 10 dB is times 10, right? 10 divided by 2 is 5. So that means 10 dB minus 3 dB is 7 dB, right? So that's the kind of way you want to think about it. Usually think about it as like abbreviation like 10 and 3 or something. And then, or sorry, like, yeah, 10 and 3, and you just kind of like mix and match those numbers together to make something close. So that's how you can do very quick calculations in your head. One more question. What is 20 milliwatts in dBm? I already asked this one. Who remembers what it was? Or actually, no, I didn't ask this one. Never mind. I asked the opposite of it.
$13.
13? Yeah. It's 13 dBm. Similarly, it's just 6 plus 7. It's 0 dBm plus 6 plus 7. So that's another way you can think about it, right? Because 20 is 4 times 5, right? So it's just 6, which is times 4, then plus 7, which is times 5, 20, right? We start with our 0 dBm. So it's pretty simple. So now we can move on to transmission lines. So finally some fun and cool stuff. Because everything before was apparently not cool. Anyway, recall 101A. Yay, my favorite class, right? Yeah. Smith you'll see those two next lecture. Yeah. I love Smith charts. Not right now though, that's too much. So let's talk about what a transmission line is real quick. So a transmission line, so I guess all conductors have a distributed inductance and capacitance per unit length. Right? So all wires are not ideal wires. When a signal propagates in a real wire, it's encountering its capacitance associated to the wires and inductance associated to the wires. So wires are not ideal. This slows down the current and voltage when you turn on the circuit, right? The capacitors have to fill. The inductors don't like current changes. So you have to kind of fill those capacitors, and the inductors resist the current, so the voltage kind of slowly propagates through the circuit. It's constrained. So voltage and current propagate through the wires as waves, right? So as our signal goes through the circuit, right, it has to kind of fill those capacitors, go through those inductors. It will just take time to go through the circuit. That's all it is. So we say they propagate as waves through the circuit. They have some sort of speed that's set by the inductance and capacitance in that circuit, right? So here's the little diagram. We have a two-conductor transmission line, right? So we measure our voltage between these two. And we just have some signal, right? That's between the lines. And yeah, it just goes through the circuit. Okay. So everything is a transmission line. So here's how to think about it, right? When I say everything is a transmission, you are a transmission line, which is very true. You're actually a very good antenna, which is fun. you can hook yourself up to an oscilloscope and see all sorts of fun, cool stuff. Like if you ever held an oscilloscope probe with your finger, you might have seen 60 hertz, right? A little sine wave looks like 60 hertz. Yeah, you're picking up the walls, like the electrical signals inside the walls, right? Nothing can like not be a transmission line, and maybe that's a little frightening. So here's another way of thinking about what a transmission line is. An antenna emits waves into free space, right? So we know this. This is kind of intuitive to all of us, right? We have currents and stuff inside of an antenna, and they're able to then emit them as electromagnetic fields, as the voltage and current in this antenna is transmuted into freely propagating electromagnetic fields. These waves can only propagate at the speed of light. So if you remember solving the wave equation of physics or something, right? There's c. Okay, it's fixed. The speed at which these waves propagate is fixed, and this actually inherently limits the ratio of the electric field and the magnetic field, right? So as you learn inherently for a given medium, the electric field is always some fixed ratio, right, to the magnetic field. That has to do with the fact that the actual wave is fixed, has a fixed velocity in that medium. Right? We call this ratio of the free space's characteristic impedance. Right? So it's a geometrical and material characteristic. Right? So if we have some antenna with some electric and magnetic field generated from it, the ratio of the electric and magnetic field is fixed. If you remember from physics, this is the ratio, the square root of the ratio of the permeability of free space to the permittivity of free space. Don't need to worry about that too much, but it's around 377 ohms or 125 ohms, if you're curious. So it means that always, whenever a wave propagating in space, like in this room, the electric field in ratio with the magnetic field, right, is 377. Okay. So electromagnetic waves can propagate along conductors. So as we just talked about, waves can propagate through space, right? We can also have them propagate around conductors, my bad. All right, so if you have two conductors, we have behavior similar to that of free space. There's a lot of nuance for what I mean by that. It means that they're TEM waves. You have to worry about exactly what that means, but it's very similar, right? The idea of impedance is very similar, right? So with the constant geometry and material, the ratio of the electric and magnetic field around conductors is completely constant. So all transmission lines have a characteristic impedance associated with them, right? The electric and magnetic field associated around these wires as it propagates through, right, has a fixed ratio. And here is a diagram of what that kind of looks like. So on the left we see just a little GIF of current, we see the charge moving around the circuit, and we can see how the amplitude is just kind of goes as a wave into this load, this impedance on the right. On the right here we have just another graph showing the voltage and the currents and how the amplitude, right, as you move along the circuit, will move through the circuit as a wave, right? And that's the actual ratio between them is fixed. Okay, so this is for like a 1.5 meter circuit with a characteristic impedance of 50 ohms. So the ratio between the voltage current is 50, and this is from 0 to 1.5 meters. Right? So with time, we see the wave just move. Okay. So now we have like a very basic, just general intuition for like what a transmission line is. It's kind of like how waves propagate through space, but now we're able to like throw in a conductor, right? So all conductors can work like this. They very, very efficiently can constrain our fields instead of going out in all directions, like from an antenna. They constrain the fields around the conductor, right? But the same rules apply. There's still this characteristic impedance. There's still a fixed velocity, right? And these waves can actually propagate. Okay, so we can terminate a transmission line with a load or an impedance. What does this really mean? So let me go ahead and show you the diagram again, right? We can essentially take a transmission line, which is like two conductors, right? So we have currents and voltage in this line propagating, and it reaches some sort of load, like a resistor, right? So the transmission line itself has its own characteristic impedance, and the load, or the resistor, for instance, has its own impedance. So if the impedance of the load is equal to the characteristic impedance of the transmission line, we say that maximum power is sent to the load. So if you remember from 110 or something, or 10, I don't actually remember which class this is, if you have a source, a voltage source, with a series resistor, and then a load resistor, the maximum power you can send from that source, right, occurs when the load resistor is equal to the series resistor on the source, right? The source resistance is equal to the load resistance. Similarly, right, the maximum power you can send to some sort of load from a transmission line only occurs when your load impedance is equal to your transmission line impedance. I'll tell you a little bit more. I'll show you actually why that's the case. So yeah, the ratio of voltage to current is constant at the load, so it looks like an infinite transmission line. I can replace this load right here with another transmission line and go on forever, and it won't notice. Because the ratio of the electric field and the magnetic field, or the voltage to the current, similarly, is constant. Okay, so if we attach a load that's not equal to the characteristic impedance, we want to see what happens, right? So as we can guess, we're not going to get full maximum power transfer. So we want to see what does that even mean? What happens? So this means that there's a difference in ratio of voltage to current at the transmission line and the load, right? So if we have a different impedance, the ratio of our voltage and currents are different. This means that a backwards propagating wave is created to ensure that this ratio is satisfied at the load. My circuit cannot make the load change its impedance. Its impedance is fixed. It's a geometric quantity, right? It's based on the material and geometry of our circuit. So the fields have to satisfy that, right? It's like a boundary condition. And what it does is it creates a wave that goes back to the source, so that the ratio of the voltage to the current is just the same as it is at the load. It's called a reflection. And the power is reflected back to the source, right? So when we're talking about maximum power transfer, when we don't have matching impedances, we have an impedance mismatch. Power is reflected back to the source. Right? So that's where the power goes. So here's a more complicated diagram showing you exactly what that means. So we have a transmission line, again like 50 ohms, and we have a load here. This load has an impedance of 0 ohms, so it's like a short. And we know the ratio of the voltage to current should be here, and it should be 0 here, right? The voltage should be 0 at a short. So that means is that this circuit needs to basically create a wave, right, that will cancel out the incident voltage. So the green right here is incident voltage. You see it travel into the load. It'll then create a wave that reflects back from this load so that it cancels the voltage right there. So the voltage, as you see, is 0. Right? So our impedance is satisfied. Right? But this means now we have reflections. So our source is actually not able to deliver any power in this case. And you can see similarly there's the current. And if we go back here, still, even though there's reflections and stuff, the voltage to the current ratio is still 30. So over here, the voltage to the current ratio is 0. Over here, it's 50. So in order to just keep the boundary conditions the same, you just need a reflected signal. Okay. So we'll talk about some specific examples. Here's some notation, a little diagram I'll show you to kind of, I guess, show you like a few examples. So we're going to have a transmission line with a characteristic impedance of Z0. We have a forward propagating wave, V plus, and a backward reflected propagating wave, V minus. We have then a load ZL at Z equals 0. Right? So just some Z equals 0. That won't matter too much to it for us right now, but just for your information. And then we have gamma, which is called our reflection coefficient. So the reflection coefficient right at the load is the following. It's just the ratio of the voltage of our reflected signal to the voltage of our forward propagating signal, right? Which through transmission line theory, you're able to derive. If you solve a bunch of differential equations, you're able to figure this out and find that it's just the difference of the impedances over the sum of the impedances, right? So this just tells you how much of a reflected signal is the relative to our forward propagating signal, right? So the maximums can actually be in a circuit is like 1, right? Realistically. Actually, cases are bigger than 1, but don't worry about that. So the reflection coefficient along the line changes. This is actually pretty important, right? So as soon as we have a mismatch over here, we have some gamma of 0. As we move along the line, the phase of it changes, right? So the phase of the V minus to V plus changes, right? But its magnitude is the same. So I'll define beta real quick. So it's just 2 pi over lambda, just the wave number. Don't worry about that. But the magnitude of the coefficient is the same across the transmission line, but the phase changes. And this makes sense if you look at back the last slide and we have this diagram. The phase has to change because you notice the forward and backward propagating waves have different phases the entire time. Anyway. Okay. So let's do a quick example. Assume that our load is an open circuit. What is our reflection coefficient? Does anyone know what this is? Can anyone tell me? So using our formula on the last slide, remember, it's ZL, the load impedance, minus the source impedance for the sum of. Let's see. 1. Yeah. So it's 1 because an open circuit is infinite impedance, right? So this means that our I would have a harder example next. I'll try that one. Okay, so essentially, our reflected voltage is just equal to our incident voltage. Right? This kind of makes sense. Okay. Interpretation. All the signals are reflected back to the source with the same polarity. That's it. So no power can be sent to open space like this if you assume it's not an antenna. If it's antenna, this is exactly what happens actually. I'll tell you about that because ideally in transmission line theory, you think this is a circuit, this is what it is, just infinite impedance. But free space actually isn't infinite impedance. So if you have a transmission like this, it will actually just turn into like kinetic waves. It's pretty cool. It's the idea of some kinds of antennas used a lot. Anyway, so no power is delivered to the load since there is no load. It's just infinite impedance. You can't just direct through the scan. Okay, let's do another example. Assume that our load is a capacitor. What is our reflection coefficient for a real characteristic impedance? So Z0 equals 50 ohms. So it's a real characteristic impedance. Can anyone tell me this? This is a little bit more tricky. It's just a little bit algebra. It's an expression too, it's not a number.
Is it 1 over z conjugate? Or
1 over z conjugate?
1 over z?
Or what?
1 over z? Or 1 over z conjugate?
Well, the units are unitless, right? So that wouldn't make sense. Yeah, for the reflection coefficient. So, I mean, yeah, something like that. So 1 minus j omega z naught c, or 1 plus j omega naught z naught c. Yeah. You just plug in the formula, right? But here's the really cool thing. The magnitude is 1. Right? So what does that mean?
No power loss.
What is power loss here? What does that mean?
Or we get all the power is reflected back.
Exactly, right? Capacitor is a reactive component. It's not a resistor. It can't dissipate, right? So a capacitor and inductor, they have to reflect all the power back to the source, right? So in interpretation, all of the signal is reflected back to the source since the load is purely reactive. And that's actually really interesting. And this is a key idea in like large-scale transmission line theory, right? Where you're doing like power distribution. If you have a factory with a bunch of motors, which are highly inductive loads, that's reactive, right? So if you just send power to a factory and it has highly inductive loads, what happens? So that power can be reflected back. You don't properly match it. So what you do is you actually get massive capacitors to cancel out that inductance so that it looks like a resistive load. So then you can actually have a better match, so you can actually power the plant, right, or the factory. Okay. Alright, so why did I do that? Two-port networks and S parameters. So now we're on to the last little bit of our presentation, and this is probably some of the most important parts. And this is something that you will see all the time in RF microwave. And it's exclusively the units and the parameters, the S parameters are exclusively used everywhere, right? You'll see them all the time. So let's briefly talk about circuits as black boxes. Okay, there is our receiver. So we have some analysis goals here, right? We want to basically build a system, a methodology, per se, to try to figure out like how to even come close to analyzing something as complicated as this, right? Just think about it, right? You have so many circuits connected to each other. How do I take one circuit, connect it to another, and hope that like my circuit's response isn't destroyed, you know, as soon as I connect something else to it? How do we like make a circuit modular? So we want to simplify the analysis of our system so it's easy to cascade devices, or have one device connect to the next and have each device still operate as they should, and do the thing that we want them to do. We need a way of almost universally characterizing a function of a circuit block. Okay, so almost because it relies on a condition, and that condition is that the circuit is LTI, very linear, in time invariant, as you know from 102. And we need a model that will allow us to abstract out the inner components of a block. Okay, so if you're familiar with 110 content, this is kind of the concept of Z and Y parameters, right? Or if you did H parameters, hybrid parameters and stuff, and all that sorts of content. If you remember doing those, it's the same idea, but we don't really use Z parameters in microwave or RF. We use something called S parameters, which we'll talk about. And they're actually a lot more intuitive to use. Okay, two-port networks. The RF system is built with two-port networks. Right? What does this mean? These are ways of these are ways of encapsulating the operation of a strictly LTI system circuit. Yeah.
What's an LTI circuit, sorry?
Okay, yeah. So if you haven't taken 102, kind of important. That means like when I said Fourier spectrum, that I meant nothing.
No.
Okay, you know Fourier analysis is, right?
Yes.
But LTI is linear time invariant, so there are two conditions on a system. Right? I'm going to say system, not circuit, because this applies to other fields. If I have a signal going into a system, and it's linear, right? It means that I can basically take two signals, put them into the system, there's some, put them in the system, and I can separate them outside, right? The system operates on each of them independently, right? So, Linear also means that, remember Taylor series, right? Linear is just like, for instance, 1 plus x is a linear function, right? The system is linear, right? It doesn't have like x squared or x cubed or x fourth times, right? It doesn't multiply things together. So it kind of separates, right? It withholds what's called homogeneity in superposition. Anyway, and time invariant just means that it doesn't matter when we use the system. If it's time varying, that means it matters when our signal goes into the system. Okay, so we have a black box, and we know this black box has 2 ports. A port is just 2 terminals, right? Because the voltage exists between 2 terminals. So the only things we can realistically measure with the 2-port is its voltages and currents, and that's exactly what I've done, like showed right there. That's all we can do, right? We can't measure anything else because we can't go into the black box, can we? So in our application, the bottom terminals of port 1 and 2 is truly grounded, right? So we just have a constant ground between all of our 2 ports. So it's like we're really looking at just 2 terminals on there. And an example of that is like our amplifier, right? So we just be measuring the input ports of our amplifier with respect to ground. So now we can talk about scattering parameters. So S parameters. Scattering is a cool name. The scattering parameters are used also not in electrical engineering, they're used kind of everywhere. They're used in optics, of course. The same idea is used in optics. They're used in quantum mechanics all the time. And this entire methodology can be kind of extended quite far. So essentially, we represent our circuit with a series of parameters, which I'll show you. And instead of looking at voltage and currents, we look at a forward propagating wave and a reflected wave in each port. Because that's what we can realistically measure in transmission line theory. Forward propagating wave and a backward propagating wave. So we'll create a 2-port model using transmission line theory, right? This model is described by scattering parameters or S parameters, more colloquially hear it. And here's the idea. For all frequencies, we send a wave to the circuit, right? So V1 plus. So for all frequencies, that means we're going to scan all frequencies and see what happens. We're going to measure how much voltage is reflected back, right? And then we're going to measure how much voltage passes through. It's V2 minus, you see right there. So you see how much voltage is reflected back and it goes in, right? That's actually one port characterized. We do the opposite, right? And we see how much is reflected back here and how much goes through this way, essentially. So that's the entire idea of scattering parameters, actually. So I'll talk a little bit more detail, but it's just looking at reflected signals and transmitted signals through the circuit. Okay. Here's our diagram again. Why is there no current in this definition? It's kind of boring. So we kind of remove the current and just have now 2 voltages. It's because when we're using S parameters, we assume a constant impedance, right? I was talking about constant impedance before in transmission lines. Transmission lines have constant impedance, right? But different transmission lines, different geometries will have different impedances. It's also important, right? But there's no current because if I know the impedance is constant, I can find the current by just dividing the voltage. That's it, right? So voltage over the impedance is just the current. So we don't need current in this definition, right? So all we really care about is this forward and backward propagating waves. So that means for all measurements, we assume there is some impedance, called Z0, connected to each port. Right? We'll always assume that's a constant impedance throughout the circuit. If we do that, as we'll see later, we'll get no reflections and it'll be really easy to measure everything. And cascade devices. And you'll hear this a lot. A very common characteristic piece is 50 ohms, right? Or 75 ohms too, if you're doing like TV stuff. Apparently, I don't know why they still use that. But 50 ohms is incredibly common because actually it's very easy to make, like geometrically. It's just a nice number. But there's no other reason for that, to be honest. It's kind of arbitrary. It's kind of 50 is cool, better than 51, I guess. But anyway. So we just assume that it's constant impedance. It's just an assumption, and all S parameters need to be defined with a characteristic impedance. I can define my S parameters with 100 ohms, 1 million ohms, or 50 ohms. But I need to specify to you what I'm identifying that impedance to be. Or else I can't find the current, right? And the current is in the circuit, so if I know what the current is, right? It was a V. Okay. So now we're gonna like mathematically describe what's going on here. So again, here's our diagram. I'm gonna write some equations that will tell you what the voltage is on each port with our actual parameters. Okay, so we have two equations here, right? And once you look at them for a little long, it's not too hard to see what's going on here, right? So the first equation at the top says V1 minus is equal to S11, just a coefficient, times V1 plus, right? So the port, this voltage right here, is equal to some scaled version of this, which makes sense, right? And it's also equal to some other coefficient times this voltage. So it's the wave propagating into the circuit and the wave propagating into the circuit this way, right? So we see how, let's say, two sources will cause a voltage V1 minus. Similarly for V2, it's the same idea. We see how the input waves into the circuits are exits this port, right? That's it. So in order to isolate these, we need to basically set up some special circuit cases to measure S11, S12, S21, S22. That's what we do right here. So the S11 is just the ratio of V1 minus and V1 plus, right? So the backward, so the reflected and forward propagating wave, assuming that there's no incident wave on here. That's really important. If there is an incident wave on here, then we're gonna get a change in V1 minus. So we can't isolate S11. So what we typically do here is just connect 50 ohms here, right? And there's no source there. It's just matched. This characteristic is V1. And so on for the rest of the parameters, right? We essentially just set V1 plus and V2 plus to 0 so that we can isolate each one of these parameters and extract out our S parameters. And we actually measure them, that's what we do. Yeah.
So you put the 50 ohms there to make it look like an infinite.
Yes, exactly, right? Because if we don't do that, we need a characteristic contains everywhere, right? We need a constant contains everywhere. It's an assumption about our system. Any other questions? Cool. Okay, so we're gonna do a very quick example, right? I'm not gonna expect anyone to do this off the top of their head. But it'll show you the kind of work that's involved in doing this by hand. It's not super bad, it's just, you know, it can be intensive, especially when you have variables. So we're gonna find S11, S21 for the following circuit, where we assume Z0 is 50 ohms. This is called a T-pad attenuator. It's called a T-pad because it looks like a T. That's it. There's also another version of it, which is actually equivalent called a pi pad. It just looks like a pi. Right? These are used everywhere. These are broadband attenuators. So what we're gonna do is we're gonna find the S11 and the S21 for this circuit, right? Okay. So, again, the S11 is just a reflection coefficient of port 1. Right? Right? Remember, it's the ratio of V1 minus to V1 plus, assuming V2 plus is 0. Right? So there's no wave propagating into the circuit from this direction. It's just 50 ohms right here. So what we do is we attach a 50 ohm node here, and then we solve the reflection coefficient into the circuit. Right? So Zin is the input resistance, assuming port 2 is terminated with C0. Right? So what we do is just find the input resistance of this circuit. Right? So as it turns out, it's just R1 plus R2 parallel R1 plus C0. Right? We just do the math. And we get about 50 ohms. So it means that the parameters of the circuit, R1 and R2, have been selected so that our input resistance still looks like 50 ohms. Which is good. We want that actually. It's great if our S11, if our input impedance looks like 50 ohms. This is just like another transmission line. We get full power matching. Right, so if we calculate S11, which is just a reflection coefficient, we use our formula, we get 0. Because they're matched. For reflection coefficient 0, all of our power goes into the circuit. Nothing's reflected back. So this is a T-pad attenuator because of the S21. So S21 is the ratio of the output to the input voltage, and port 2 is terminated with Z0. So it's just this voltage to this voltage, pretty simple to find, right? So very quickly do that. We get 1 over square root of 2. Right? So this is an attenuator where the output voltage is just 1 over square root 2 of the input voltage. That's it. Alright, so if you go and do the math yourself and everything, verify it for yourself, you'll see this is exactly what happens. So we found our S11 and our S21, right? And I talked about, for all frequencies earlier, by the way. So if a circuit has capacitors and inductors or other fancy stuff, then you need to account for omega. There'd be like or F in our output, so it might be frequency dependent. Okay, so let's actually talk about S11 and S21. Talk about like what they mean, especially in the circuit's context. So as it turns out, the reflection coefficient is equal to S11 generally. This makes it very intuitive for us, right? We're simply finding the ratio of reflected image to incident voltage of port 1. That's it. There's a similar intuitive understanding of S21. It's the ratio of output voltage traveling out of port 2 compared to the incident voltage of port 1. It's the voltage gain of the circuit, right? If the voltage out is less than the voltage in, it's more like a loss, right? Like in the last example, we say that the circuit attenuates our signal. That's why it's called an attenuator. We can still call it a gain, which is a small, right? Less than 1. Okay, so a measurement device doesn't directly find any of the S parameters, right? In terms of voltages. That's really important. Is that once we get to really high frequencies, it's really hard to measure a voltage. If you think about it, it's the ways that we measure like ACs and stuff. You can't do it. So instead we find is phase and power. It's actually really easy to find power. You use a diode. Actually, it's usually what happens. And you use some fancy interferometric stuff or whatever. I don't know. You can find its phase, right? So you're able to find the phase of a coefficient and its power. That's usually what you see on a vector network analyzer, which measures S parameters. So S1 represents reflected power. S21 represents forward transmitted power. Right? So now we're getting to a definition that makes more sense in the measuring world, where instead of talking about voltages, we're talking about power. Right? So reflected power and we have transmitted power. The average power of steady-state signal is the following, as we've seen a little bit earlier. Right? So if we extend this to S parameters, the ratio of reflected power to incident power is the following, right? Since this is the ratio of voltages, we just find it's just the magnitude squared of our S11, right? And similarly for S21, which is the magnitude squared, right? So we don't have to do much to find it. Because we have a constant impedance, that's what matters. Alright, that's what happens. Anyway, so decibels, we get this. And again, it's 20 log because S parameters are defined in terms of voltages, right? So again, just remember that. It's 20 log if the absolute value of S11 and S21 has to be the absolute value too, or else, some funky stuff can happen. Okay. So in the example of the T-FET attenuator from earlier, we call it a 3 dB attenuator, right? Because the S21 is 1 over square root 2, but in dB, which is minus 3 dB. So our signal is subtracted, has its amplitude, or power is subtracted by 3 dB, right? Or half. Okay? So these are exact kinds of measurements our vector network analyzer gives us. Right? With just S11 and S21, we can fully characterize the performance of an LTI network using RAC, right? In one direction, right? So if there's S12 and S22, you might be wondering, well, if I have an amplifier, I don't really care about what happens if I put a signal at the output and figure out what happens, the transmitted power into the input, right? That's an important parameter, by the way. That is still very important, but for most applications, though, we care about how much power is transmitted through and gained, and how much power is reflected back from the input. Okay. So we can characterize filters, amplifiers, and attenuators, and we'll go more in depth on how to make such measurements in the next lecture. So here's just an example of me measuring the 27 MHz bandpass filter that's used in our circuit. Right? On the left is our bandpass filter used with discrete inductors and capacitors, and our right is the vector network analyzer. What this does is it actually injects waves into the circuit. A reflected wave comes back and measures that reflected wave. And then a wave is transmitted through, right? So it comes out here, goes into the circuit, comes back, and the through port, it allows us to measure the S21. So if we go ahead and look more closely, right, we see that this is a filter, right? So our transmitted power, we would expect to see, you know, this kind of bandpass filter response, right, over frequency. And this is frequencies on this horizontal axis, and magnitude is on the vertical axis. And this is exactly what we see. We see a filter response. And then, so that's the blue there, right? And you'll notice that's in dB. So dB is used everywhere, so you have to get used to it. And you'll notice that's in the yellow there is the S1 low, right? And in the pass band, so we see the least amount of attenuation in our signal, we would expect the S1 to be small, right? Or negative, very negative. So we see these little dips right here, and it's below some like minus 10 dB in this case, right? So that means only 10% of our power is actually reflected back to the source, which is nice. So 90% of the power actually makes it through the loop. It's not a perfect match, but it's like good enough, right? Usually a good enough match is like minus 15 dB S11, minus 10 dB S11. If you're not working in megawatts. If you're working in megawatts, it's deadly. You need like minus 40 dB. But anyway, so it's pretty cool. We can look at another example. So here is a bandpass filter from mini circuits, and this is what their data sheet says. You'll notice that they have insertion loss and return loss. Don't worry about group delay. I'll explain what that means really quickly. But so this is a filter you can buy from them. It's 50 ohms, as you can see, and it's 3.1 gigahertz to 3.5 gigahertz. Right? So its pass band is from 3.1 gigahertz to 3.5 gigahertz. And this is the insertion loss. So insertion loss is just the S21. Right? This is how we define insertion loss and return loss. Insertion loss is just minus S21 dB. You notice the axis is positive and it goes down. It's kind of weird. And then the return loss is just the S1, the reflection coefficient. That's it, right? The group delay is just how long it takes a signal at a certain frequency to go through the circuit, right? In nanoseconds. We don't really care about that too much for our application. Okay, and very quickly, the last part, just cascading, right? So if the S11 and the S22 of our 2 ports are all 0, right? It means they're all matched, right? There's no reflections, right? We say they're matched, it's not. So that means we can cascade them without changing their characteristics, right? If I have a circuit that's matched to 50 ohms, and I attach a 50 ohm transmission line to it, there you go. All the power can come from the circuit into the transmission line as backup. If I put another circuit that's also 50 ohms, it doesn't know if there's another circuit there, or it doesn't know if there's a circuit there or a transmission line. It's still 50 ohms. It doesn't care, right? So our circuit's matched. Its response, everything the circuit does is kept the same. Right? So we typically want all of our circuits to be matched to 50 ohms, so that their responses stay the same. They operate exactly at how we want them to. Okay, so this allows us to easily find what happens to a signal as it propagates through our circuit. We can represent every circuit's S21 as a gain, negative or positive, represented by G. Right? So this is incredibly important. So S21, just the power gain. So if our first circuit has an S21 of G1, our second circuit has S21 of G2, we multiply them together, and we find the power delivered to the load is G1 times G2 times the power of the source. Very, very simple. That's why S parameters are so cool, because it's really easy to look at a circuit and kind of know what happens to the signal as it goes through it. You can also account for phase with it too. Remember, S parameters are not just magnitudes, they're also phases. They also are complex numbers, so they represent phase. Finally, using decibels, to find the power at some point in the circuit, you just add all the gains up until that point, plus the source power. What do I mean? In dB, right? We add all the gains, and if gains are negative, that means it's a loss, obviously, right? Like if you have a T5 attenuator, we can find the power delivered to the load. And that's it, right? So this is the Friese equation. You might have seen this in 101B. Same thing for like antenna links and stuff. You know, the gains of the antennas, you have path loss and everything. The same equation is used, right? When dealing with our circuits, you look through your signal path and you see how the signal goes up in amplitude, goes down in amplitude, changes phase, and whatever. And you see, you can characterize exactly what happens at the outputs for it. Okay. And that's basically it for scattering parameters. So I'll post an article on Discord. We won't get too long, just kind of reviewing generally the content. It's pretty straightforward. Content's not super hard. There's DSP